Okay, so let's start with one of my favorite facts. Did you know that the universe contains 2 trillion galaxies? Each a glittering city of billions of stars, far outnumbering the grains of sand on all Earth's beaches. This staggering count reveals a universe teeming with worlds beyond imagination. So settle in, and let's explore the science behind this cosmic census and what it tells us about our place in the vastness. This estimate came from the Hubble Space Telescope's deep space observations, particularly the Hubble Ultra Deep Field, which peered 13 billion light-years into the past. In 2016, astronomers led by Christopher Consolis used these images to count galaxies, extrapolating to the entire observable universe. They found 2 trillion galaxies, 10 times more than previously thought, each containing 100 billion to a trillion stars, dwarfing Earth's sandy shores. On galaxies vary widely. Some, like our Milky Way, are spirals with 100 billion stars, while others are massive ellipticals or tiny dwarfs. The Sloan Digital Sky Survey mapped over 1 million galaxies, revealing their diversity in size, shape, and star content. This survey, combined with Hubble's deep fields, showed that the universe is a vast mosaic, with galaxies clustering in filaments, walls, and voids. And counting galaxies is no simple task. Telescopes capture light from distant galaxies, some so faint they're barely visible. By analyzing their brightness and redshift, astronomers estimate their distance and number. The 2016 study used gravitational lensing, where massive galaxy clusters bend light, magnifying fainter galaxies. This revealed countless small, distant galaxies, boosting the total count to 2 trillion, more than sand grains on Earth's beaches. And this number reflects only the observable universe. A sphere 93 billion light-years across, limited by the distance light, has traveled since the Big Bang. Beyond this horizon, more galaxies likely exist, possibly infinitely many, if the universe is infinite. The cosmic microwave background, studied by the Planck satellite, shows a uniform universe, suggesting galaxies are spread evenly on large scales. Supporting this massive estimate, NNTHE galaxies themselves are dynamic. Each hosts billions of stars, along with planets, black holes, and nebulae. Star formation, driven by collapsing gas clouds, fills galaxies with light, while supernovas and black holes shape their evolution. The James Webb Space Telescope observes galaxies from the universe's infancy, revealing how they formed and grew over 13 billion years. This vast number has profound implications. With 2 trillion galaxies, the potential for planets and even life is staggering. If each galaxy has 100 billion stars and many have planets, the universe could host trillions of worlds, some perhaps habitable. This fuels the search for exoplanets, with missions like TESS identifying thousands of candidates, hinting at the cosmos's diversity. The count also informs cosmology. Galaxies trace the universe's structure, forming in regions seeded by Big Bang fluctuations. The Vera C. Rubin Observatory will map billions more galaxies, refining our estimate and revealing how dark matter and dark energy shape their distribution. This cosmic census connects us to the universe's history, from its fiery birth to its sprawling present. Okay, next up. The largest structure in the universe is a wall of galaxies, a structure so immense it dwarfs our imagination. The Hercules Corona Borealis Great Wall, a colossal web of galaxies stretching over 10 billion light-years, stands as the largest known object in the cosmos. Discovered in 2013, this galactic monument holds billions of Milky Ways, a testament to the universe's vast architecture. This massive structure was found using data from the Swift and Fermi gamma-ray telescopes, which detected an unusual clustering of gamma-ray bursts, explosions tied to massive stars. These bursts, mapped across the constellations Hercules and Corona Borealis, revealed a region packed with galaxies, spanning 10 billion light-years, about 1/10 the observable universe. This wall, far larger than any known supercluster, contains countless galaxies, each with billions of stars, bound loosely by gravity in a filamentary structure. The universe is organized into a cosmic web, filaments, walls, and voids shaped by gravity over billions of years. The Hercules Corona Borealis Great Wall is the largest of these walls, a sprawling network of galaxy clusters stretching across space. Its discovery came from analyzing gamma-ray bursts, which act like cosmic beacons, pinpointing regions dense with star-forming galaxies. The wall's size challenges our models of cosmic structure, as such a massive formation pushes the limits of how galaxies can clump together. Each galaxy in this wall is like our Milky Way, home to 100 billion stars or more. Billions of these galaxies, strung together like pearls, form a structure so vast it could hold billions of Milky Ways, a scale that defies comprehension. The wall's density is still sparse, with vast spaces between galaxies, but its gravitational pull holds it together, resisting the universe's expansion driven by dark energy. The wall's discovery relied on statistical analysis. Gamma-ray bursts produced by supernovas or merging neutron stars trace regions of high galaxy density. The 2013 study, led by Istvan Horvath, found an excess of bursts in a specific sky region, suggesting a structure far larger than expected. Follow-up observations with optical telescopes confirmed the presence of numerous galaxies, forming a filament that spans billions of light years. This structure tells us about cosmic evolution. After the Big Bang, 13.8 billion years ago, tiny density fluctuations in the early universe grew under gravity, forming filaments and walls. The cosmic microwave background, mapped by the Planck satellite, shows these initial fluctuations, which seeded structures like this wall. Its immense size suggests it formed early, when the universe was denser, allowing galaxies to cluster on such a grand scale. Why is this wall so significant? It challenges the cosmological principle, the idea that the universe is uniform on large scales. A structure this large hints at unevenness, prompting questions about how it formed within the universe's age. Some theories suggest it's a statistical fluke, while others propose new physics, like variations in dark matter distribution, to explain its existence. Future observations will refine our understanding. The Vera C. Rubin Observatory, set to begin operations in 2025, will map billions of galaxies, potentially revealing more about this wall's structure. The James Webb Space Telescope can study its distant galaxies, probing their star formation and composition. These efforts will clarify whether this wall is truly the largest, or if even bigger structures lurk unseen. The wall also connects to the universe's fate. As dark energy drives expansion, structures like this may stretch and disperse, with galaxies drifting apart. Yet, for now, the wall stands as a gravitational anchor, a cosmic monument binding billions of galaxies across an unimaginable expanse. Okay, time for another cool fact now. Did you know that neutron stars are denser than mountains? Let's shrink the unimaginable to the size of a teaspoon. Neutron stars, the remnants of massive stars, are so dense that a single teaspoon of their material would weigh as much as Mount Everest, about 6 billion tons. These cosmic relics, born from catastrophic explosions, pack incredible mass into a tiny sphere, defying our sense of reality. Neutron stars form when a massive star, 8 to 20 times the Sun's mass, exhausts its fuel and collapses in a supernova. The core, compressed by gravity, becomes a neutron star, a sphere just 20 kilometers wide, but with the mass of 1 to 2 suns. This density is staggering. A single teaspoon of neutron star material, heavier than a mountain, contains matter so tightly packed that atoms are crushed into a sea of neutrons. The physics of this density is extreme. In a neutron star, gravity squeezes protons and electrons together, forming neutrons in a process called neutronization. The resulting material, called neutronium, is 1 billion times denser than any substance on Earth. If you could hold a teaspoon of it, it would weigh as much as Mount Everest, about 6 billion tons, making it impossible to lift or contain outside the star's gravity. Neutron stars are studied through their emissions. Many spin rapidly, emitting beams of radio waves, as pulsars, detected by telescopes like the Arecibo Observatory. The Crab pulsar, born in a 1054 supernova, spins 30 times per second, its density revealed by its precise pulses. X-ray telescopes, like NASA's Chandra, Observe neutron stars in binary systems, where their gravity pulls material from a companion, heating it to millions of degrees. The internal structure of these stars is a mystery. The outer crust, made of compressed iron nuclei, gives way to a core of exotic matter, possibly quark-gluon plasma or strange matter. This core, where density peaks, is so extreme that a teaspoon's worth could outweigh entire mountain ranges. Theories suggest the core may even form a crystalline lattice, or a fluid of free neutrons, defying our understanding of matter. Observations confirm this density. In 2017, the LIGO Observatory detected gravitational waves from two merging neutron stars, revealing their masses and sizes. The event, in Galaxy NGC 4993, showed neutron stars are so dense that their collisions release energy equivalent to billions of suns. The NICER telescope on the International Space Station measures neutron star sizes, confirming their compactness, with surfaces so dense they warp space-time. This density has cosmic implications. Neutron stars test Einstein's relativity, as their gravity bends light and time, similar to black holes. They also produce heavy elements, like gold and uranium, forged in their cores or during collisions, scattered across the universe. The gold in your jewelry may have come from a neutron star's crushing density, a gift from a cosmic forge. Future missions will probe deeper. The square-kilometer array under construction will detect thousands of pulsars, refining our models of neutron star interiors. Experiments like those at CERN simulate extreme densities, offering clues to neutronium's nature. These studies reveal how matter behaves at its limits, bridging astrophysics and particle physics. Moving on. Now, time for the hottest place in the universe, which is a quasar. Quasars, powered by supermassive black holes, can reach temperatures of 10 billion degrees Fahrenheit, hotter than any star's core, as they devour matter and blaze like a trillion suns. These radiant beacons light up the universe with ferocious energy. Quasars are among the universe's most luminous objects, found at the hearts of distant galaxies, where supermassive black holes, millions to billions of times the sun's mass, consume gas and dust. As this material spirals inward, it forms an accretion disk, heating to extreme temperatures through friction and compression. The quasar 3C273, visible in Virgo, shines with the light of a trillion suns, its disk reaching 10 billion degrees Fahrenheit, dwarfing the 27 million degrees of the sun's core. This heat comes from gravitational energy. As matter falls toward the black hole, it accelerates to near-light speeds, colliding and compressing in the accretion disk. This converts gravitational potential into thermal energy, producing temperatures hotter than any stellar core. X-ray telescopes, like NASA's Chandra, detect this heat through high-energy emissions, revealing the quasar's intense environment. The light, spanning radio to gamma rays, travels billions of light-years, making quasars visible from the universe's youth. Quasars were most common when the universe was young, 2 to 3 billion years after the Big Bang, when galaxies were gas-rich and black holes fed voraciously. The Sloan Digital Sky Survey has cataloged over 500,000 quasars, showing their peak activity in this early era. Their heat, driven by accretion, makes them the hottest natural objects known, far surpassing supernovas or stellar cores. The physics of this heat is extreme. The accretion disk, spinning at relativistic speeds, emits X-rays and ultraviolet light as matter rubs together, reaching temperatures where atoms are stripped into plasma. Some quasars also produce jets, streams of particles accelerated to near-light speed, adding to their radiant output. These jets, seen in quasars like PKSO 637-752, can stretch millions of light-years, carrying heat and energy across galaxies. Observations confirm these temperatures. The James Webb Space Telescope studies quasars from the early universe, detecting infrared signatures of their hot disks. The Event Horizon Telescope, imaging black hole shadows, reveals the warped spacetime around quasars, where heat is generated. These observations show that a quasar's core is a furnace no material could withstand, vaporizing anything that ventures too close. Quasars also shape their galaxies. Their intense radiation can halt star formation by heating or ejecting gas, regulating a galaxy's growth. The elements forged in these processes, like carbon and oxygen, are scattered by jets or outflows, enriching the cosmos. Quasars, blazing like a trillion suns, are cosmic engines, driving the evolution of galaxies across billions of years. Future telescopes, like the Extremely Large Telescope, will probe quasar environments in greater detail, mapping their disks and jets. These studies will reveal how black holes grow and how their heat influences the universe's structure. Quasars, as the hottest places known, offer a window into the extreme physics of gravity and matter. Okay, next up, what is the coldest place in the universe? We're going to venture into a realm colder than the darkest voids of space for this one. The Boomerang Nebula, 5,000 light-years away, holds the title of the coldest known natural place, at -458 degrees Fahrenheit, a cosmic freezer chilling even the emptiness of space. This icy wonder results from gas expanding at incredible speeds. The Boomerang Nebula in the constellation Centaurus was discovered in 1980 by the Anglo-Australian Telescope and studied in detail by the Atacama Large Millimeter Array. Its temperature, just 1 Kelvin above absolute zero, is colder than the cosmic microwave background at 2.7 Kelvin, which bathes the universe in faint warmth. This extreme cold comes from the nebula's rapid expansion, as gas is ejected from a dying star at 164 kilometers per second. The nebula formed when a star, nearing the end of its life, shed its outer layers, creating a cloud of gas and dust. This star, likely once similar to our Sun, became a white dwarf, expelling material in a bipolar outflow, giving the nebula its boomerang-like shape. As the gas expands outward, it cools dramatically, a process called adiabatic cooling, where pressure drops and temperature plummets, creating a cosmic freezer colder than Antarctica or even empty space. This cooling is driven by physics. When gas expands rapidly, its molecules spread out, reducing collisions and lowering energy, which translates to colder temperatures. In the Boomerang Nebula, gas moves 10 times faster than typical planetary nebulae, amplifying this effect. Radio telescopes, like ALMA, detect the nebula's cold gas through its faint millimeter-wave emissions, confirming its record-breaking chill. The nebula's temperature is remarkable. At -458 degrees Fahrenheit, it's colder than liquid helium used in labs to approach absolute zero. The cosmic microwave background, the Big Bang's afterglow, sets a baseline temperature for space, but the Boomerang's rapid expansion beats even that. This makes it the coldest natural place known, though artificial experiments, like Bose-Einstein condensates, reach even lower temperatures in labs. Observations reveal more about its structure. The nebula spans about a light-year, with a dense core and 2 lobes of gas resembling an hourglass. The Hubble Space Telescope captured its glowing edges where starlight reflects off dust. The central white dwarf, still hot at thousands of degrees, contrasts with the surrounding gas, creating a stark temperature gradient within a single system. This coldness has cosmic significance. Nebulae, like the Boomerang, enrich the universe with elements like carbon and oxygen, ejected by dying stars. These elements, cooled in the nebula's icy expanse, may seed new stars and planets, contributing to the cosmic cycle. The nebula's chill also tests our understanding of stellar evolution, showing how dying stars create extreme environments. Future telescopes, like the James Webb Space Telescope, will study the nebula's composition, probing its cold gas for clues to its formation. These observations will clarify how such extreme temperatures arise, and whether other nebulae could be even colder. The Boomerang Nebula stands as a unique laboratory, revealing the universe's capacity for icy extremes. Okay, the next fact is one of my favorites. A black hole can spaghettify you. Crazy, right? We're going to approach a cosmic force so powerful it reshapes matter itself. Near a black hole, extreme gravity stretches objects into thin strands, a process called spaghettification, turning a human into cosmic noodles before they reach the event horizon. This bizarre phenomenon reveals the relentless pull of gravity's extremes. Black holes, formed from collapsed stars or merging black holes, have gravity so intense that not even light escapes. Their event horizon marks the point of no return. But before crossing it, objects face tidal forces, where gravity varies across their structure. For a human falling toward a black hole, the feet, closer to the center, feel stronger gravity than the head, stretching the body into a long, thin strand like cosmic noodles pulled apart by an unseen force. This effect comes from tidal forces, described by Einstein's general relativity, which shows how gravity warps spacetime. Near a stellar mass black hole, 10 to 30 times the sun's mass. Tidal forces are so strong that spaghettification occurs well outside the event horizon. For a 70-kilogram human, these forces would tear the body apart in milliseconds, long before reaching the black hole's core. The process is observed indirectly. In 2020, the Zwicky Transient Facility detected a star being spaghettified by a supermassive black hole, 215 million light-years away. As the star was stretched and torn, it formed a glowing accretion disk, emitting X-rays and optical light. Telescopes like NASA's Chandra captured these tidal disruption events, where stars are shredded into streams, confirming spaghettification's reality. The strength of spaghettification depends on the black hole's size. Smaller black holes with tighter event horizons have stronger tidal forces, shredding objects far from the horizon. Supermassive black holes, like the 4 million solar mass one in the Milky Way, have gentler tidal gradients, allowing objects to approach closer before being stretched. For a human, though, the result is the same, a transformation into a cosmic thread. This phenomenon reveals black holes' power. The Event Horizon Telescope's 2019 image of a black hole showed space-time warping that enables spaghettification. The gravitational pull, increasing exponentially near the event horizon, stretches matter while compressing it sideways, creating a noodle-like shape. This process releases energy as torn-apart matter heats up, glowing brightly before vanishing into the black hole. Spaghettification also connects to cosmic evolution. Stars shredded by black holes contribute to accretion disks, fueling quasars or X-ray binaries. The debris, rich in heavy elements, may be ejected, enriching galaxies with material for new stars. This violent process shapes the universe, turning matter into energy and light. Future observations will probe deeper. The Vera C. Rubin Observatory will detect more tidal disruption events, revealing how common spaghettification is. These events test relativity, showing how gravity distorts matter and spacetime. Spaghettification, though deadly, offers a window into the extreme physics of black holes. Moving on to the largest star, which is 1,700 times bigger than the Sun. Dealing with some big numbers here, guys. It's kind of a cosmic titan. Iconus, a red supergiant in the constellation Cepheus, is so massive that it could engulf Jupiter's orbit, with a diameter 1,700 times that of the Sun. One of the largest stars known, it dwarfs our solar system with its immense size. Iconus, also known as UY Scuti, spans about 2.4 billion kilometers, making it 1,700 times wider than the Sun. If placed at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and Jupiter's orbit, reaching nearly to Saturn. This red supergiant, 9,500 light-years away, is a star nearing the end of its life, bloated by the exhaustion of its nuclear fuel. Red supergiants form when massive stars, 8 to 40 times the Sun's mass, burn through their hydrogen and helium, swelling as their cores contract. Iconus, estimated at 10 to 30 solar masses, has expanded as it fuses heavier elements, like carbon and oxygen, in its core. Its surface, cooler at 3,000 Kelvin compared to the Sun's 5,500 Kelvin, glows red, giving it a distinctive hue visible through telescopes like the Very Large Telescope. Measuring Iconus's size is challenging. Its diameter was estimated using interferometry, combining light from multiple telescopes to resolve its bloated shape. The Gaia satellite, mapping stellar distances, refined its distance, confirming its enormous size, at 1,700 solar diameters. Iconus could engulf entire planets, a scale that makes our Sun seem minuscule by comparison. Despite its size, Iconus is less dense than the Sun. Its outer layer is a diffuse gas, puffed up by radiation pressure, but its core, where fusion occurs, is incredibly dense, producing energy that drives its expansion. This star, nearing a supernova, will one day collapse and explode, scattering elements like iron and gold across the cosmos. Iconis isn't alone. Other red supergiants like Betelgeuse and Antares approach similar sizes, though Iconis holds the record. These stars, observed by Hubble and the James Webb Space Telescope, show complex atmospheres with mass loss creating dusty shells. Iconis loses material equivalent to Earth's mass yearly, forming a nebula that may seed future stars. The star's size has cosmic implications. Its eventual supernova could outshine its galaxy, releasing energy to forge heavy elements. These explosions shape galaxies, enriching them with material for planets and life. Iconis, as a cosmic giant, plays a key role in this cycle, its size a prelude to its explosive end. Future observations will clarify Iconis's fate. The extremely large telescope, under construction, will study its atmosphere, revealing how such massive stars evolve. These studies will show whether Iconis remains the largest, or if even bigger stars await discovery, hiding in distant galaxies. Alright, moving on. Did you know that voids are emptier than empty? Cosmic voids, vast regions between galaxy clusters. Are nearly empty, with less than 1 atom per cubic meter, making them emptier than empty. Stretching millions of light years, these voids are the universe's quietest places, a stark contrast to its starry realms. Cosmic voids are the low-density regions of the universe's structure, the gaps in the cosmic web of filaments, walls, and clusters. Discovered through galaxy surveys, like the Sloan Digital Sky Survey, they occupy 60 to 80% of the universe's volume, with sizes ranging from 10 to 100 million light-years. The Boots void, one of the largest, spans 250 million light-years, containing fewer galaxies than expected, with a density emptier than empty space. This emptiness is extreme. In a typical void, you'd find less than 1 atom per cubic meter, compared to 100 trillion atoms per cubic meter in Earth's air. This sparsity comes from the universe's evolution, where gravity pulled matter into dense filaments and clusters, leaving voids behind. The cosmic microwave background, mapped by the Planck satellite, shows the seeds of these voids, as regions of low density grew into vast, empty spaces. Voids are studied through galaxy distribution. The 2 Decipherod's Galaxy Redshift Survey mapped millions of galaxies, revealing voids as regions with few or no galaxies. Their emptiness is relative. Some contain faint dwarf galaxies or wisps of gas, but their density is so low they're nearly invisible. Telescopes like Hubble detect these sparse regions by their lack of light, a negative space defined by the absence of stars. The physics of voids is tied to dark energy. As the universe expands, voids grow larger, as dark energy pushes matter outward, emptying them further. The lambda-cold dark matter model predicts that voids dominate the universe's volume, with their growth accelerating over time. Observations of galaxy motions show matter streaming from voids into denser regions, like water draining from a sink. Voids also affect cosmology. Their size and distribution. Test models of dark matter and dark energy, which shape the cosmic web. The Euclid mission, launched in 2023, maps voids in 3D, revealing their structure and evolution. These studies show how voids, though empty, influence the universe's expansion, acting as counterweights to dense clusters. The emptiness has implications for life. Voids, with few stars or planets, are unlikely to host life, unlike dense galaxy clusters. Yet, their study reveals the universe's balance, where emptiness and density coexist, shaping its structure. The Boots void, for example, challenges theories, as its extreme emptiness suggests unusual formation processes. Future surveys, like the Vera C. Rubin Observatory, will map more voids, refining our understanding of their role. These empty regions, though sparse, hold clues to the universe's past and future, revealing how matter and energy interplay across cosmic scales. Okay, here's another cool fact for you. Supernovas outshine entire galaxies. A supernova, the explosive death of a massive star, can briefly shine brighter than an entire galaxy, releasing energy equal to the sun's lifetime output in mere seconds. These cosmic fireworks illuminate the universe with dazzling brilliance. Supernovas occur when massive stars, 8 to 20 times the Sun's mass, exhaust their fuel and collapse, triggering a catastrophic explosion. This collapse, in milliseconds, compresses the star's core, releasing a shock wave that blasts its outer layers into space. The resulting burst, shining like 100 billion suns, can outshine an entire galaxy of billions of stars, visible across billions of light-years. There are two main types. Type 2 supernovas from massive stars explode when their cores collapse into neutron stars or black holes. Type Ia supernovas occur in binary systems, where a white dwarf accretes mass and ignites in a thermonuclear blast. Both types, observed by telescopes like Hubble, release energy equivalent to the Sun's 10 billion-year output in seconds, creating a cosmic fireworks show. Historical supernovas, like the one in 1054 that formed the Crab Nebula, were visible in daylight, recorded by ancient astronomers. Modern telescopes, like the Zwicky Transient Facility, detect dozens of supernovas yearly, their light curves revealing their energy and distance. The 1987A supernova in the Large Magellanic Cloud was the closest in centuries, offering a detailed look at this explosive process. The energy comes from nuclear and gravitational forces. In a Type 2 supernova, the core's collapse releases neutrinos, carrying away 99% of the energy, while the rest powers the visible explosion. Type Ia supernovas, triggered by carbon fusion, produce a uniform brightness, making them standard candles for measuring cosmic distances. Their light, detected by the James Webb Space Telescope, reveals the universe's expansion. Supernovas shape the cosmos. They forge heavy elements, like iron and gold, scattering them into space to form new stars and planets. The gold in your ring likely came from a supernova's fiery end. They also trigger star formation, as shockwaves compress gas clouds, sparking new stellar births in galaxies like the Milky Way. Their brilliance has practical uses. Type Ia supernovas, with consistent brightness, helped discover the universe's accelerating expansion in 1998, earning a Nobel Prize. The Vera C. Rubin Observatory will detect thousands more, refining our understanding of dark energy. Supernovas, outshining galaxies, are cosmic beacons, guiding our study of the universe's fate. Okay, another fun fact. The universe's biggest explosion was a hypernova. So let's kind of marvel at the universe's most colossal blast. Hypernovas, rare explosions of massive stars, release 100 times more energy than a typical supernova, potentially powering gamma-ray bursts that light up the entire universe across billions of light-years. These cataclysmic events are the cosmos's most powerful outbursts. Hypernovas occur when stars over 30 times the Sun's mass collapse into black holes, triggering an explosion far more energetic than a standard supernova. First identified in the 1990s, they produce gamma-ray bursts, the brightest events known, detectable by telescopes like NASA Swift. A hypernova in 2003, GRB030329, shone across 2.6 billion light-years, its energy dwarfing entire galaxies. The explosion is driven by extreme physics. As the star's core collapses, it forms a rapidly spinning black hole, surrounded by an accretion disk. This disk, heated to millions of degrees, launches jets of plasma at near light speed, emitting gamma rays that can light up the entire universe. These jets, if aimed at Earth, appear as brilliant flashes, lasting seconds to minutes, followed by an afterglow. Gamma-ray bursts are key to studying hypernovas. The Fermi Gamma Ray Space Telescope detects their high-energy emissions, revealing their power. A single hypernova releases energy equivalent to 100 supernovas, or the Sun's output over 10 trillion years in mere seconds. This energy, mostly in gamma rays and neutrinos, can ionize gas across galaxies, affecting star formation. Hypernovas are rare, occurring in massive stars with high metallicity, or in binary systems where mergers trigger collapse. The Eta Carinae system, 7,500 light-years away, may produce a hypernova in the future, offering a front-row seat. Their rarity makes each detection crucial, with observatories like Chandra capturing their X-ray afterglows, revealing their structure. These explosions shape the cosmos. They forge heavy elements like uranium and plutonium, scattering them to form new stars and planets. The 2017 kilonova from merging neutron stars showed similar processes, but hypernovas are far more energetic, producing the universe's heaviest elements. Their jets can trigger star formation or disrupt galaxies, altering their evolution. Future missions, like the Athena X-ray Observatory, will study hypernova remnants, probing their black holes and jets. These observations will clarify how hypernovas form and how their bursts influence the universe's structure. As the biggest explosions known, they offer a glimpse into the extreme physics of stellar death. Okay, moving on. Let's talk about all things quantum now. Let's take a look at the universe's most colossal blast now. Hypernovas, rare explosions of massive stars, release 100 times more energy than a typical supernova, potentially powering gamma-ray bursts that light up the entire universe across billions of light years. These cataclysmic events are the cosmos's most powerful outbursts. So settle in, and let's explore the science behind hypernovas and their radiant impact. Hypernovas occur when stars over 30 times the sun's mass collapse into black holes, triggering an explosion far more energetic than a standard supernova. First identified in the 1990s, they produce gamma-ray bursts, the brightest events known, detectable by telescopes like NASA's SWIFT. A hypernova in 2003, GRBO 30329, shone across 2.6 billion light-years, its energy dwarfing entire galaxies. The explosion is driven by extreme physics. As the star's core collapses, it forms a rapidly spinning black hole surrounded by an accretion disk. This disk, heated to millions of degrees, launches jets of plasma at near-light speed, emitting gamma rays that can light up the entire universe. These jets, if aimed at Earth, appear as brilliant flashes, lasting seconds to minutes, followed by an afterglow. Gamma-ray bursts are key to studying hypernovas. The Fermi Gamma-ray Space Telescope detects their high-energy emissions, revealing their power. A single hypernova releases energy equivalent to 100 supernovas, or the sun's output over 10 trillion years, in mere seconds. This energy, mostly in gamma rays and neutrinos, can ionize gas across galaxies, affecting star formation. Hypernovas are rare, occurring in massive stars with high metallicity, or in binary systems where mergers trigger collapse. The Eta Carinae system, 7,500 light-years away, may produce a hypernova in the future, offering a front-row seat. Their rarity makes each detection crucial, with observatories like Chandra capturing their X-ray afterglows, revealing their structure. These explosions shape the cosmos. They forge heavy elements, like uranium and plutonium, scattering them to form new stars and planets. The 2017 kilonova from merging neutron stars showed similar processes, but hypernovas are far more energetic, producing the universe's heaviest elements. Their jets can trigger star formation or disrupt galaxies, altering their evolution. Future missions, like the Athena X-ray Observatory, will study hypernova remnants, probing their black holes and jets. These observations will clarify how hypernovas form and how their bursts influence the universe's structure. As the biggest explosions known, they offer a glimpse into the extreme physics of stellar death. As we press on in this cosmic exploration, picture a hypernova's radiant blast lighting up the entire universe. These colossal explosions reveal a cosmos where the deaths of stars create bursts of light and matter, shaping the galaxies we see today. Okay, so for this one, we're going to step into a realm where reality bends in ways that defy our senses. Quantum superposition allows particles, like electrons, to exist in multiple states simultaneously, dancing in two places at once until an observation pins them down. This strange behavior challenges everything we know about the world. Superposition is a cornerstone of quantum mechanics, the theory governing the subatomic world. An electron, for instance, can occupy multiple positions or energy states at the same time, described by a mathematical wave function. Until measured, it's not in one place, but in all possible places, a ghostly blend of realities. When observed, the wave function collapses, forcing the particle to choose one state, as if reality snaps into focus. This was first proposed in the 1920s by physicists like Erwin Schrödinger, who used it to explain atomic behavior. The famous Schrödinger's cat thought experiment illustrates this, imagining a cat both alive and dead until observed. In real experiments, like those with electrons in atom traps, superposition is confirmed, with particles detected in multiple states until a measurement, like a laser pulse, fixes their position. How does this work? The wave function is a probability cloud, describing where a particle might be. In the double-slit experiment, electrons fired at two slits create an interference pattern, as if each electron passes through both slits simultaneously, existing in two places at once. Detectors, like those at CERN, show this pattern vanishes when one slit is watched, proving observation shapes reality. Superposition's implications are profound. It underpins quantum technologies, like quantum computers, which use superpositioned qubits to perform millions of calculations at once. In nature, photosynthesis in plants may rely on superposition as molecules explore multiple energy paths to transfer sunlight efficiently. This suggests the universe operates on a probabilistic stage, where certainty emerges only when we look. The phenomenon challenges classical physics. Isaac Newton's laws assume objects have definite positions, but quantum mechanics reveals a fuzzier reality. Experiments at the Large Hadron Collider observe particles like quarks in superposed states, their properties undefined until measured. This fuzziness extends to cosmic scales, where early universe fluctuations seen in the cosmic microwave background were superposed states shaping galaxies. Why can't we see this in everyday life? Quantum effects fade at larger scales, a process called decoherence, where interactions with the environment collapse the wave function. A macroscopic object, like a ball, interacts with countless particles, fixing its state. But in isolated systems, like ultra-cold atoms, superposition persists, allowing particles to dance in multiple realities. Future experiments will probe deeper. Quantum telescopes, under development, aim to detect superposition in larger systems, testing its limits. Projects like the quantum experiments at space scale explore superposition in orbit, free from Earth's noise. These efforts could reveal whether superposition holds at cosmic scales, linking the quantum and the cosmic. All right, now let's venture beyond the world we know, into realms unseen. String theory proposes the universe could have 11 dimensions, most curled up so tiny they're invisible, yet holding the key to unifying all of physics. These hidden dimensions reshape our understanding of reality's fabric. String theory, developed in the 1980s, seeks to reconcile Einstein's relativity with quantum mechanics. It suggests that particles, like electrons, are not points, but tiny vibrating strings, whose patterns determine their properties. For these vibrations to work mathematically, the universe must have extra dimensions beyond the familiar 3 of space and 1 of time, up to 11 in some models, like M theory. These extra dimensions are compactified, curled into shapes smaller than a trillionth of a meter, far below what our instruments, like the Large Hadron Collider, can detect. These shapes, called Calabi-Yau manifolds, are complex, multidimensional structures, folding the extra dimensions into intricate geometries. Each configuration determines the laws of physics, from gravity's strength to particle masses. Why 11 dimensions? Early string theory proposed 10, but M theory, unifying 5 string theories, added an 11th, allowing a consistent framework. This model predicts phenomena like supersymmetry, where each particle has a partner, potentially detectable at accelerators like CERN. If true, these hidden dimensions could explain why gravity is weaker than other forces, perhaps leaking into extra dimensions. Evidence is indirect. The Large Hadron Collider searches for signs, like missing energy from particles escaping into extra dimensions, but none have been found yet. The cosmic microwave background, mapped by the Planck satellite, shows no clear signs of extra dimensions, but their tiny scale makes them elusive. String theory's math remains a compelling guide, predicting phenomena like black hole behavior with uncanny accuracy. The implications are vast. If 11 dimensions exist, our universe might be one of many in a multiverse, each with different physical laws defined by its dimensional geometry. The anthropic principle suggests our universe's laws are fine-tuned for life, possibly because we exist in a dimension-friendly configuration. This reshapes cosmology, linking the quantum to the cosmic. Experiments probe these ideas. The ATLAS and CMS experiments at CERN search for supersymmetric particles, which could hint at extra dimensions. Future gravitational wave detectors, like LISA, might detect dimensional effects in black hole mergers. These tests could confirm string theory, revealing a universe woven from hidden realms. The concept also inspires technology. String theory's math informs quantum computing and advanced materials, where high-dimensional models optimize performance. If extra dimensions exist, they could unlock new physics, from faster-than-light communication to unified theories of gravity and quantum mechanics. Now, let's connect across the vastness of the cosmos. Quantum entanglement links particles so their states are intertwined, where measuring one instantly affects the other, even across light years, a phenomenon Einstein dubbed spooky action at a distance. This cosmic connection defies our understanding of space and time. Entanglement occurs when two particles, like photons, interact and share a quantum state. Their properties like spin or polarization becoming correlated. Measuring one particle's state instantly sets the others, no matter the distance. This was proposed in 1935 by Einstein, Podolsky, and Rosen in their EPR paradox, questioning whether quantum mechanics was complete or if hidden variables explained the link. Experiments confirm this strangeness. In 1982, Alain Aspect's team entangled photons and measured their polarizations miles apart, showing instant correlations faster than light could travel. The Bell test experiments ruled out hidden variables, proving entanglement's reality. Modern tests, like those at Delft University in 2015, entangled electrons 1.3 kilometers apart, closing loopholes with precise measurements. How does it work? Entangled particles share a single wave function, a mathematical description that collapses when one is measured, fixing both states. This doesn't transmit information faster than light, as the outcome is random, preserving relativity. Yet, the spooky action suggests a deeper connection, perhaps through quantum non-locality, where space itself doesn't limit their bond. Entanglement's reach is cosmic. In 2017, Chinese scientists entangled photons and sent one to a satellite 1,200 kilometers away, confirming the link holds over vast distances. In theory, particles entangled in the early universe could remain connected across billions of light years, their states tied from the Big Bang to now. The phenomenon drives technology. Quantum computers, like those by IBM, use entanglement to link qubits, enabling complex calculations. Quantum cryptography secures data with entangled particles, as any eavesdropping disrupts the link. Future networks, like the quantum internet, could use entanglement for unhackable communication, connecting Earth to satellites or beyond. Entanglement also probes cosmology. The cosmic microwave background contains entangled photons from the Big Bang, potentially testable with advanced detectors. Black holes, studied by the Event Horizon Telescope, may preserve entanglement in their Hawking radiation, offering clues to quantum gravity. This connection bridges the subatomic to the cosmic, revealing a unified universe. Future experiments will push further. The Quantum Entanglement Space Experiment aims to test entanglement in orbit, free from Earth's interference. Detectors like those at LIGO could find entangled gravitational waves, linking quantum mechanics to spacetime. These efforts explore whether entanglement is the universe's secret messaging system, binding reality across vast distances. As we continue this cosmic journey, Picture entangled particles whispering across the stars, a spooky action binding them as one. This cosmic connection reveals a universe where distance is no barrier and particles share a dance that spans the cosmos. Now let's peer into a universe that shifts under our gaze. The observer effect in quantum mechanics reveals that observing a particle, like an electron, alters its behavior, changing just because you looked. Until observed, it exists as a wave of possibilities, only taking shape when measured. The observer effect stems from quantum mechanics' wave-particle duality, where particles like electrons exist as probability waves, described by a wave function. Before measurement, an electron's position is a spread of possibilities, not fixed. Observing it, with tools like a photon detector, collapses the wave function, forcing the particle into one state, as if reality chooses a path when watched. This was demonstrated in the double-slit experiment, where electrons fired at two slits create an interference pattern, acting like waves. Place a detector at one slit, and the pattern vanishes, with electrons behaving as particles, changing just because you looked. Experiments at facilities like NIST confirm this, showing measurement itself shapes the outcome, a hallmark of quantum strangeness. Why does observation matter? Measurement interacts with the particle, whether by photons, electrons, or other probes, disturbing its state. This isn't about human consciousness, but physical interaction, as even automated detectors cause collapse. Heisenberg's uncertainty principle ties to this, limiting how precisely we can know a particle's properties, like position and momentum, simultaneously. The effect has been tested rigorously. In 1998, the Weizmann Institute used interferometers to observe quantum interference, showing that partial measurements partially collapse the wave function. Delayed choice experiments, like those by John Wheeler, show that even choosing to observe after a particle passes a slit alters its past behavior, as if time itself bends to the observer's choice. This phenomenon shapes technology. Quantum cryptography relies on the observer effect, as eavesdropping on a quantum key disrupts it, revealing intrusion. Quantum computers use controlled measurements to manipulate qubits, preserving their delicate states. These applications, developed by companies like Google, show the observer effect's practical power, turning quantum weirdness into tools. Cosmically, the effect raises questions. In the early universe, quantum fluctuations, now seen in the cosmic microwave background, were waves of possibility. Their collapse, perhaps triggered by cosmic interactions, shaped the galaxies we see today. The James Webb Space Telescope studies these fluctuations, hinting at how observations sculpted the cosmos from a quantum haze. Future experiments will probe deeper. Quantum sensors, like those in LIGO, could test the observer effect at larger scales, exploring where quantum mechanics meets classical reality. Projects like the quantum reconstruction of objects aim to observe quantum effects in macroscopic systems, challenging our understanding of when observation matters. Now, guys, let's slip through the barriers of the impossible. Quantum tunneling allows particles to pass through obstacles, like cosmic ghosts gliding through solid walls, by borrowing energy in the quantum realm. This defies classical physics and powers the universe's strangest tricks. Quantum tunneling arises from the wave-like nature of particles described by quantum mechanics. A particle, like an electron, exists as a probability wave with some chance of being beyond a barrier, like a wall or energy field, even if it lacks the energy to cross classically. This wave can leak through, allowing the particle to appear on the other side, as if passing through a hill instead of over it. This was first explained in the 1920s by physicists like George Gamow, who applied it to nuclear decay. In alpha decay, particles escape a nucleus, despite being trapped by a strong nuclear force, tunneling out with a small probability. Experiments at facilities like Oak Ridge National Laboratory confirm this, measuring decay rates that match tunneling predictions, proving particles can defy barriers. The mechanism relies on the wave function, which extends beyond barriers, giving a non-zero chance of finding the particle there. The Heisenberg uncertainty principle allows particles to briefly borrow energy, enabling them to cross forbidden regions. In scanning tunneling microscopes, electrons tunnel through tiny gaps, imaging atoms with precision, a technology that earned a Nobel Prize in 1986. Tunneling is vital in nature. In the Sun, protons tunnel through electrostatic barriers to fuse, powering stellar energy. Without tunneling, fusion would be too slow, and stars, including our Sun, wouldn't shine. Laboratory experiments, like those at the National Ignition Facility, replicate this, showing tunneling's role in nuclear reactions that fuel the cosmos. The phenomenon has cosmic reach. In the early universe, quantum tunneling may have driven inflation, a rapid expansion triggered by a field tunneling to a lower energy state. The cosmic microwave background shows hints of this, with fluctuations possibly shaped by tunneling events. Black holes, studied by the Event Horizon Telescope, may lose mass via Hawking radiation, where particles tunnel out of the event horizon. Tunneling powers technology. Flash memory in USB drives relies on electrons tunneling through insulators, storing data. Quantum computers use tunneling to manipulate qubits, enhancing their speed. Future applications, like quantum tunneling transistors, could revolutionize electronics, making devices faster and more efficient by exploiting this ghostly passage. Future experiments will explore further. The Large Hadron Collider searches for tunneling in high-energy particle interactions, testing quantum field theory. Projects like the Deep Underground Neutrino Experiment probe tunneling in neutrino oscillations, linking it to cosmic mysteries. These studies reveal how tunneling shapes the universe, from stars to subatomic realms. All right, moving on. Let's talk about a universe where certainty slips away. Heisenberg's uncertainty principle declares that you cannot know a particle's position and speed precisely at the same time, a game of hide and seek where the more you learn about one, the less you know about the other. This fundamental rule governs the quantum world's elusive nature. Proposed by Werner Heisenberg in 1927, the uncertainty principle is a pillar of quantum mechanics. It states that certain pairs of properties, like position and momentum, are linked, so measuring one with precision makes the other uncertain. Mathematically, this is expressed as delta x asterisk delta p is greater than or equal to c/2, where c is Planck's constant, a tiny value setting the quantum scale. This isn't about measurement flaws, but a fundamental limit of nature. Experiments confirm this. In 1927, Heisenberg's thought experiments showed electrons scattering light, blurring their position or momentum. Modern tests, like those at the Max Planck Institute, use laser-cooled atoms to measure position precisely. Finding momentum becomes unpredictable, creating a fuzzy cloud of probability. This hide-and-seek defines how particles behave, from atoms to photons. Why does this happen? Particles exist as wave functions, probability waves that spread out, encoding possible states. Measuring position collapses the wave, narrowing its location but spreading its momentum, and vice versa. The double-slit experiment shows this, with electrons forming interference patterns when unmeasured, but fixed paths when observed, their momentum uncertain. The principle shapes the universe. In atoms, electrons orbit in probability clouds, their positions uncertain, stabilizing atoms like those in your body. In the early universe, quantum fluctuations, governed by uncertainty, seeded galaxy formation, visible in the cosmic microwave background mapped by Planck. These fluctuations were uncertain in energy and time, shaping the cosmos' structure. Uncertainty drives technology. Quantum cryptography uses the principle to secure data, as measuring a quantum state disturbs it, revealing eavesdroppers. Quantum computers exploit uncertainty to create superposed states, enabling vast calculations. Experiments at IBM and Google harness this, showing how uncertainty fuels innovation, turning quantum limits into power. Cosmically, uncertainty has profound effects. Black holes emit Hawking radiation due to uncertainty in energy near the event horizon, potentially causing their evaporation. The Large Hadron Collider probes uncertainty in particle collisions, revealing how it governs fundamental interactions. The principle links the subatomic to the cosmic, defining reality's boundaries. Future experiments will push deeper. Quantum sensors, like those in gravitational wave detectors, test uncertainty at extreme scales, exploring its role in spacetime. Projects like the quantum-enhanced imaging aim to use uncertainty for ultra-precise measurements, from atoms to stars. These efforts reveal how uncertainty weaves the universe's fabric. Next, let's dive into the fizzing heart of the cosmos. At the smallest scales, space isn't smooth, but bubbles with quantum foam, a turbulent sea of fluctuations where particles pop in and out like a cosmic soda. This fleeting chaos shapes the very nature of reality. So let's explore the science behind quantum foam and its role in the universe's smallest realms. Quantum foam was proposed by John Wheeler in 1955, combining quantum mechanics and general relativity. At scales below 10 to the power of minus 35 meters, the Planck-length space becomes a frothy mix of virtual particles and energy fluctuations, driven by Heisenberg's uncertainty principle. Energy and time, uncertain at tiny scales, allow particles to appear and vanish in fractions of a second, creating a fizzy, unstable space. This arises from quantum field theory, which describes particles as excitations in fields, like ripples on a pond. In the vacuum, these fields fluctuate, producing virtual particles, like electrons and photons, that exist briefly before annihilating. The Casimir effect, observed in 1948, confirmed this, showing metal plates pushed together by virtual particles outside them, proving the vacuum's lively nature. Quantum foam's effects are subtle but real. In particle accelerators, like CERN's Large Hadron Collider, high-energy collisions reveal virtual particles contributing to scattering processes. The Lamb shift, a tiny energy shift in hydrogen atoms, is caused by virtual particles tugging on electrons, measurable with spectroscopy. This foam underpins the quantum world, making space alive with energy. Cosmically, quantum foam has profound implications. In the early universe, fluctuations at the Planck scale, amplified during inflation, seeded cosmic structures visible in the cosmic microwave background. Black holes may interact with quantum foam, as Hawking radiation relies on virtual particles tunneling out of the event horizon. The Event Horizon Telescope probes these effects, linking foam to cosmic phenomena. The foam challenges our view of space. General relativity assumes a smooth spacetime, but quantum foam suggests a turbulent, probabilistic fabric at tiny scales. String theory proposes that foam is shaped by extra dimensions, with vibrating strings creating its texture. These ideas aim to unify quantum mechanics and gravity, a holy grail of physics. Future experiments will seek evidence. Gravitational wave detectors, like LIGO, could detect foam's effects on spacetime ripples, though current sensitivity falls short. Quantum sensors, like those in the Fermi National Accelerator Laboratory, probe vacuum fluctuations, testing foam's properties. These efforts could reveal whether space truly fizzes like a cosmic soda, shaping reality's foundation. Technology may harness this. Quantum computers exploit vacuum fluctuations to enhance calculations, while future energy systems could tap zero-point energy, though this remains speculative. Quantum foam offers a glimpse into a universe where emptiness is alive, buzzing with potential at every point. As we continue this cosmic journey, picture space fizzing like a cosmic soda, alive with invisible sparks. This quantum foam reveals a universe where even the void pulses with energy, a restless sea beneath the stars. Now, let's watch the universe blur into waves of possibility. In quantum mechanics, particles like electrons can behave as waves, rippling like water and interfering with themselves, as shown in the double-slit experiment. This dual nature redefines our understanding of matter. Wave-particle duality, proposed in the early 20th century, is a cornerstone of quantum mechanics. Louis de Broglie suggested in 1924 that particles, like electrons, have wave-like properties with wavelengths tied to their momentum. The double-slit experiment fires electrons at two slits, creating an interference pattern on a screen, as if each electron ripples like water through both slits at once. This was first confirmed in 1927 by Clinton Davison and Lester Germer, who observed electrons diffracting like waves off a crystal. Modern experiments like those at the University of Vienna show even large molecules, like buckyballs, creating wave patterns, proving duality extends beyond tiny particles. When observed at a slit, the wave collapses, and electrons act as particles, a shift tied to measurement. The mechanism lies in the wave function, a mathematical description of a particle's state, spreading out like a wave. This function encodes probabilities, allowing a particle to exist in multiple states, interfering with itself. In the double-slit setup, unmeasured electrons form bands of constructive and destructive interference, a hallmark of wave behavior seen in labs worldwide. Duality shapes the universe. In atoms, electrons exist as standing waves, forming orbitals that define chemical bonds. The sun's fusion relies on protons behaving as waves, tunneling through barriers to fuse. The cosmic microwave background shows quantum fluctuations as wave-like patterns, shaping galaxies, as mapped by the Planck satellite. The phenomenon drives technology. Electron microscopes use electron waves to image atoms, achieving resolutions impossible with light. Quantum computers exploit wave-like superposition to process data, with companies like D-Wave harnessing interference for calculations. These applications turn duality into tools, revealing matter's hidden nature. Cosmically, duality raises questions. If particles are waves, could macroscopic objects show wave behavior? Decoherence, where environmental interactions collapse waves, hides this in everyday life, but experiments with ultra-cold atoms push the boundary. The Large Hadron Collider probes duality in high-energy particles, linking it to fundamental forces. Future tests will explore further. Quantum interference experiments aim to test duality in larger systems, like viruses, challenging where quantum meets classical. Space-based experiments, like the Cold Atom Laboratory, study wave behavior in microgravity, free from Earth's noise. These efforts could reveal how duality shapes reality, from atoms to stars. Now, let's envision a mind that thinks like the cosmos itself. Quantum computers use superposition and entanglement to process information in ways classical computers can't, potentially cracking the universe's code by simulating its most complex systems. This revolutionary technology promises to unlock cosmic mysteries. Unlike classical computers, which use bits as zeros or ones, quantum computers use qubits, which can be 0, 1, or both simultaneously, thanks to superposition. Entanglement links qubits, creating correlations that allow parallel computations. A quantum computer with 300 qubits could represent more states than atoms in the observable universe, a power demonstrated by Google's Sycamore in 2019, achieving quantum supremacy. How do they work? Qubits, often supercooled atoms or photons, are manipulated with quantum gates, using lasers or magnetic fields. Superposition allows qubits to explore multiple solutions at once, while entanglement ensures their states are coordinated, solving problems like factoring large numbers exponentially faster than classical machines. IBM's quantum systems show this, solving complex algorithms in seconds. The potential is vast. Quantum computers could simulate molecular interactions, revolutionizing drug design, as seen in experiments by companies like Rigetti. They could optimize logistics, solving problems with billions of variables, or crack encryption, as Shor's algorithm threatens current cybersecurity. In cosmology, they could model the early universe, simulating quantum fluctuations seen in the cosmic microwave background. Current systems are small but growing. Google's 53-qubit Sycamore performed a task in 200 seconds that would take a supercomputer 10,000 years. IBM's 127-qubit Eagle pushes toward error-corrected systems, vital for practical use. Challenges like decoherence, where qubits lose their quantum state, are being tackled with cryogenic cooling and error correction, advancing the field rapidly. Cosmically, quantum computers could simulate black holes, testing Hawking radiation or string theory's predictions. The Large Hadron Collider generates vast data which quantum algorithms could analyze, uncovering new particles. Future systems, like those planned by IONQ, aim to model complex systems, from galaxy formation to dark matter interactions, unlocking the universe's code. The technology has limits. Quantum computers excel at specific tasks, like optimization or quantum simulations, but not general computing. Scalability remains a hurdle, with noise and errors growing as qubits increase. Yet, advances in topological qubits promise robust systems, potentially revolutionizing fields from materials science to artificial intelligence. Future developments will accelerate. The Quantum Computing for the Quantum Universe Initiative aims to model cosmic phenomena, while global efforts, like China's Zhejiang, push optical quantum computing. These machines could one day simulate the entire universe, revealing its deepest secrets, from the Big Bang to the present. Now, let's peer into the void and find it teeming with life. The quantum vacuum isn't empty but buzzes with virtual particles, popping in and out of existence, fueled by quantum energy fluctuations, a void alive with cosmic energy. This restless emptiness kind of shapes the universe's very essence. Quantum field theory describes the vacuum as a sea of fields, each associated with particles like electrons or photons. Heisenberg's uncertainty principle allows energy to fluctuate briefly, creating virtual particles that appear and annihilate in trillionths of a second. These particles, though fleeting, fill every point in space, making the vacuum a dynamic, buzzing realm. The Casimir effect, discovered in 1948, provides evidence. Two uncharged metal plates placed close together are pushed by virtual photons outside them, as fewer can exist between due to wavelength constraints. Experiments at the University of Amsterdam measured this force, confirming the vacuum's energy. The Lamb shift in hydrogen atoms also shows virtual particles tweaking electron orbits, detectable with precision spectroscopy. This vacuum energy has cosmic impact. In the early universe, quantum fluctuations, amplified during inflation, seeded cosmic structures, visible in the cosmic microwave background mapped by Planck. Black holes emit Hawking radiation, where virtual particle pairs near the event horizon become real, reducing the black hole's mass. The Event Horizon Telescope probes these effects, linking the vacuum to cosmic phenomena. The vacuum's energy, called zero-point energy, is theoretically infinite but cut off at the Planck scale, as string theory suggests. This energy drives the cosmological constant, linked to dark energy, accelerating the universe's expansion. Observations by the Dark Energy Survey show this expansion, hinting at the vacuum's role in shaping the cosmos's fate. Technology taps this energy indirectly. Quantum computers exploit vacuum fluctuations to maintain qubit states, while Casimir effect experiments inform nanotechnology. Speculative ideas, like zero-point energy extraction, remain unfeasible, but the vacuum's properties inspire new physics, from quantum sensors to advanced materials. Future experiments will probe deeper. The Large Hadron Collider searches for vacuum effects in particle collisions, testing quantum field theory. Gravitational wave detectors, like LISA, could detect vacuum fluctuations in spacetime, linking the quantum vacuum to gravity. These efforts reveal a universe where emptiness is a lively stage for cosmic drama. The quantum vacuum challenges our intuition. What seems empty is a cauldron of potential, spawning particles and energy at every point. This discovery, from quantum pioneers like Paul Dirac, redefines nothingness, showing that even the void is alive with the universe's pulse. Okay guys, and now I propose we kind of travel back to the moment when everything began. Some 13.8 billion years ago, during the Big Bang, all matter and energy were compressed into a singularity, a speck tinier than a grain of sand, with infinite density. From this point, space, time, and the universe itself erupted into existence. The Big Bang marks the universe's origin, a moment when everything, every star, galaxy, and atom, was squeezed into a state smaller than an atom, a singularity where the laws of physics, as we know them, break down. This wasn't an explosion into space, but the creation of space itself, expanding rapidly from a point of unimaginable density and temperature, hotter than 1 trillion suns. The Planck satellite mapped the aftermath, showing a universe born in this fiery crucible. What was the singularity? It's not a place, but a condition, where density and energy were infinite, described by general relativity. Quantum mechanics suggests, at scales below 10 to the power of minus 35 meters, space-time itself may have been a frothy quantum foam, blurring the singularity's nature. We can't probe this moment directly, but the cosmic microwave background, detected by telescopes like COBE, offers clues, showing the universe's state 380,000 years later. The expansion began in an instant. Within 10 to the power of minus 36 seconds, the universe grew from subatomic to macroscopic, driven by a process called inflation, which we'll explore later. This rapid stretch smoothed out irregularities, setting the stage for galaxies to form. The Wilkinson microwave anisotropy probe measured tiny fluctuations in the early universe, seeds that grew into the cosmic structures we see today. The Big Bang's evidence is everywhere. The universe's expansion, observed by Edwin Hubble in 1929, shows galaxies moving apart, implying a common origin. The abundance of light elements like hydrogen and helium matches predictions from Big Bang nucleosynthesis, confirmed by observatories like Keck. These elements, forged in the first minutes, form the building blocks of stars and planets. The theory also predicts a cooling universe. At its birth, temperatures reached 10 to the power of 32 Kelvin, but as space expanded, it cooled, allowing particles to form. Quarks and gluons combined into protons and neutrons, which later fused into nuclei. By 380,000 years, electrons joined nuclei, forming neutral atoms, letting light stream free, creating the cosmic microwave background we detect today. This origin story shapes cosmology. The James Webb Space Telescope peers at galaxies from just 200 million years after the Big Bang, revealing how early structures formed. Future missions, like the Simons Observatory, will refine CMB measurements, probing the singularity's echoes. These studies deepen our understanding of how a speck became the cosmos. The Big Bang also raises profound ideas. If everything began in a point, was there a before? Some theories, like loop quantum cosmology, suggest a bounce, where a collapsing universe sparked the expansion. Others, like string theory, propose a multiverse, with our Big Bang as one of many. These ideas stretch our imagination, linking the cosmic to the quantum. And now moving on, let's look into the distant future, where the cosmos faces its fate. In trillions of years, stars may burn out, leaving a cold, dark universe, fading into icy silence as expansion continues, driven by dark energy. This scenario, known as the Big Freeze, paints a stark end to the cosmic story. The Big Freeze, or heat death, arises from the universe's accelerating expansion, discovered in 1998 through observations of distant supernovas. Dark energy, a mysterious force, makes up 68% of the universe's energy, pushing galaxies apart faster each day. As space stretches, matter and energy dilute, cooling the cosmos to near absolute zero, where motion itself slows to a halt. Stars have finite lives. Our sun, in 5 billion years, will swell into a red giant, then fade into a white dwarf, cooling over billions more. Massive stars explode as supernovas, leaving neutron stars or black holes. But even these remnants dim. In 100 trillion years, star formation will cease as gas clouds deplete, leaving a universe of dead stars observed by models like those from the Dark Energy Survey. What happens next? White dwarfs, neutron stars, will cool into black dwarfs, emitting no light. Black holes, via Hawking radiation, will evaporate over googolls of years, releasing faint particles. By 10 to the power of 100 years, only a sparse sea of photons, neutrinos, and stray particles will remain too far apart to interact, a frozen void mapped by theoretical cosmology. Dark energy's role is key. Observations of supernovas, like those by the Hubble Space Telescope, show it dominates the universe's dynamics, unlike gravity, which slows expansion. If dark energy persists, the Big Freeze is likely, but if it weakens, other fates, like a big crunch, are possible. The DESI experiment probes dark energy's behavior, seeking clues to this outcome. The Big Freeze challenges our view of time. In this era, entropy, the measure of disorder, reaches its maximum, halting all processes. Quantum fluctuations, tiny energy shifts, might spark rare events like Boltzmann brains, fleeting, self-aware structures. But these are speculative. The universe, in essence, becomes a static, unchanging expanse, studied by physicists like Roger Penrose. This fate reshapes cosmology. The Planck satellite's data suggests a flat universe, favoring endless expansion over collapse. Future telescopes, like the Vera Rubin Observatory, will map galaxy distributions, testing whether dark energy's strength holds. These observations could confirm the Big Freeze or reveal surprises, rewriting the cosmic endgame. The scenario also sparks philosophical wonder. A universe that began in fire might end in cold, its stories lost to darkness. Yet, some theories propose cycles, where new universes arise from quantum seeds, suggesting our Big Freeze is one chapter in an eternal saga. These ideas stretch our understanding of existence itself. Okay, time for another cool fact. Let's listen to the oldest light in the cosmos. The cosmic microwave background, or CMB, is faint radiation from 380,000 years after the Big Bang, a snapshot of the universe's baby picture when it cooled enough for light to travel freely. This glow is the earliest signal we can detect. The CMB formed when the universe was young, a hot, dense plasma where photons bounced off charged particles trapped in a cosmic fog. At 380,000 years, the universe cooled to 3,000 Kelvin, allowing electrons and protons to form neutral atoms, freeing photons to stream across space. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation, now cooled to 2.7 Kelvin, fills the sky. The CMB is uniform but not perfectly so. Tiny fluctuations, mapped by the COBEE satellite in 1992, show temperature variations of 1 part in 100,000 seeds of future galaxies. These ripples, caused by quantum fluctuations in the early universe, stretched during inflation, were later detailed by the Planck satellite, revealing the universe's composition. 5% matter, 27% dark matter, 68% dark energy. Why is it microwave radiation? As the universe expanded, the photons stretched, shifting from visible light to microwaves, detectable by radio telescopes like the Atacama Cosmology Telescope. The CMB spectrum, a perfect black-body curve, matches Big Bang predictions, ruling out alternative models like steady-state theory, a triumph for cosmology. The CMB's discovery was accidental. Penzias and Wilson, using a Bell Labs antenna, found persistent noise uniform across the sky, initially mistaking it for equipment error. Theorists like Robert Dicke recognized it as the Big Bang's afterglow, earning a Nobel Prize in 1978. This signal confirms the universe had a hot, dense beginning, reshaping our cosmic story. The CMB probes fundamental physics. Its polarization, studied by experiments like BICEP 2, reveals gravitational waves from inflation, if confirmed. The power spectrum, analyzed by Planck, measures the universe's curvature, suggesting a flat geometry. These data constrain models of dark energy, inflation, and the universe's fate, linking the ancient to the modern. Future missions will dig deeper. The Simons Observatory will map the CMB with unprecedented precision, seeking signs of primordial neutrinos. The Lightbird satellite aims to detect inflation's fingerprints, refining our view of the Big Bang. These efforts peel back layers of cosmic history, revealing the universe's first moments. The CMB also connects to galaxy formation. Its fluctuations grew under gravity, forming cosmic webs of galaxies, observed by the Sloan Digital Sky Survey. These structures, spanning billions of light years, trace back to the CMB's tiny ripples, showing how the universe's baby picture shaped its adulthood. Okay, guys, Now let's look into a time when the cosmos was kind of shrouded in mystery. After the Big Bang, the universe was a hot, dense plasma, a cosmic fog so thick that light couldn't pass through. It took 380,000 years to cool enough for atoms to form, letting light escape. So let's explore the science behind this opaque era and how the universe unveiled itself. In its infancy, the universe was a seething plasma, a soup of protons, electrons, and photons, hotter than a million suns. Photons, particles of light, were constantly scattered by free electrons, making the cosmos opaque, like trying to see through dense fog. This state, lasting 380,000 years, is known as the recombination era, though no atoms had existed before to recombine. The transition began as the universe expanded, cooling to about 3,000 Kelvin, the temperature of a red-hot star. Electrons slowed enough to bind with protons, forming neutral hydrogen atoms, a process captured in models by cosmologists like Jim Peebles. With fewer free electrons, photons could travel freely, turning the universe transparent, an event called decoupling. This moment is frozen in the cosmic microwave background, the light released when atoms formed, detected by the WMAP satellite. Before decoupling, the universe's opacity hid its early history, like a curtain drawn across the Big Bang. The CMB at 2.7 Kelvin today is our earliest glimpse, a snapshot of the cosmos at 380,000 years old. Why was it opaque? In a plasma, charged particles interact strongly with light, scattering it in all directions. The Saha equation, used in astrophysics, predicts when ionization drops, allowing atoms to form. Observations of the CMB's spectrum by the FIRAS instrument confirm this transition, showing a universe shifting from plasma to neutral gas. The opaque era shaped the cosmos. Quantum fluctuations, born in the Big Bang, were preserved in the plasma, becoming the seeds of galaxies. As seen in Planck's satellite data, the universe's composition, mostly hydrogen with traces of helium set during this time, matches Big Bang nucleosynthesis predictions observed in ancient stars by the Keck telescope. This period also probes particle physics. The plasma's behavior depends on interactions between quarks, leptons, and bosons, tested indirectly at the Large Hadron Collider. Neutrinos, decoupling earlier at 1 second post-Big Bang, carry hints of this era, potentially detectable by experiments like DUNE. These studies connect the opaque universe to fundamental forces. Future telescopes will reveal more. The James Webb Space Telescope observes galaxies from just after this era, showing how stars lit up the transparent cosmos. The Square Kilometer Array will map hydrogen from the pre-recombination epoch, probing the fog's edge. These efforts illuminate the universe's hidden youth. Okay, another cool concept now. Cosmic inflation. A brief, exponential expansion just after the Big Bang stretched the universe from subatomic to grapefruit-sized in 10 to the power of minus 32 seconds, ballooning faster than a blink. This surge smoothed the cosmos, setting its structure. So let's explore the science behind inflation and its role in the universe's uniformity. Proposed by Alan Guth in 1980, inflation solves puzzles in Big Bang cosmology, like why the universe appears flat and uniform. Between 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, a hypothetical field, the inflaton, drove space to expand faster than light, doubling in size every 10 to the power of minus 34 seconds. This stretched quantum fluctuations into the seeds of galaxies seen in the cosmic microwave background. Inflation's speed was staggering. The universe, smaller than a proton, grew to macroscopic scales, perhaps meters across, in a fraction of a second. This didn't violate relativity, as space itself expanded, not objects within it. The Planck satellite CMB data supports inflation, showing a flat universe with fluctuations matching inflationary predictions. Why did it happen? The inflaton field, akin to dark energy, had negative pressure, causing repulsive gravity, modeled by André Linde's chaotic inflation. When the field decayed, its energy converted into particles and radiation, reheating the universe, sparking the hot Big Bang. This transition left ripples in space-time potentially detectable as gravitational waves by experiments like BICEP 3. Inflation explains cosmic uniformity. Without it, distant regions, never in contact, shouldn't share the same temperature, yet the CMB shows they do. Inflation stretched a tiny, uniform patch across the observable universe, solving the horizon problem. Observations by the Atacama Cosmology Telescope confirm this homogeneity, bolstering inflation's case. The theory also predicts a multiverse. Different regions of space may inflate with varying physical laws, creating bubble universes, a concept from eternal inflation. While untestable directly, the math, grounded in string theory, suggests our cosmos is one of many. The Simons Observatory seeks indirect clues, probing inflation's energy scale. Inflation's fingerprints are subtle. The CMB's power spectrum shows a slight tilt, matching inflationary models measured by Planck. Gravitational waves, if detected by future experiments like LIGHTBIRD, would confirm inflation's dynamics, revealing space-time's primordial ripples. These tests bridge quantum mechanics and cosmology, uniting the small and vast. The idea reshapes our cosmic view. Inflation turned a quantum speck into the cosmos, setting the stage for stars and galaxies. Future missions, like the Cosmic Origins Explorer, will refine our understanding, probing the universe's first instant. This surge is the spark that made the cosmos possible. Let's move on to the next fact. Let's imagine a cosmos that reverses its course. If gravity overcomes dark energy, the universe might halt its expansion and collapse into a dense point, a reverse Big Bang called the Big Crunch, shrinking back to nothing. Current evidence favors endless expansion, but this possibility lingers. The Big Crunch depends on the universe's density and the balance between gravity, pulling matter together, and dark energy, pushing it apart. If the density exceeds a critical value, gravity could slow expansion, then reverse it, causing galaxies, stars, and atoms to collapse into a singularity. Einstein's general relativity predicts this, modeled by Alexander Friedmann in the 1920s. Early observations suggested a crunch was possible. In the 1980s, astronomers measured galaxy motions, estimating the universe's mass. If dense enough, gravity would win. But the 1998 supernova discoveries by teams using the Hubble Space Telescope revealed dark energy's dominance, accelerating expansion. The Planck satellite supports this, suggesting a flat, expanding universe, but uncertainties remain. What would a big crunch look like? Galaxies would merge as space contracts, heating the cosmos. Stars would collide, and black holes would coalesce, forming supermassive singularities. In the final moments, temperatures would soar to Big Bang levels, crushing matter into a point, perhaps triggering a new cycle, as proposed by cyclic cosmology models. The idea hinges on dark energy's behavior. If it weakens over time, gravity could regain control, a scenario tested by the DESI experiment, mapping galaxy distributions. Some theories, like phantom dark energy, predict a big rip, tearing space apart, but others allow a crunch. The Vera Rubin Observatory will refine these measurements, probing the universe's fate. Cyclic models add intrigue. Roger Penrose's conformal cyclic cosmology suggests a big crunch could spark a new Big Bang, with each cycle leaving imprints, like CMB anomalies. While speculative, these ideas connect the end to the beginning, suggesting an eternal cosmos. The Simons Observatory searches for such signs, testing cyclic theories. The Big Crunch reshapes cosmology. It requires a closed universe, curved like a sphere, unlike the flat geometry observed by Planck. If dark matter or unknown forces tip the balance, a crunch becomes possible. Future gravitational wave detectors, like LISA, could probe early universe conditions, hinting at collapse scenarios. The concept also sparks wonder. A universe that expands, then contracts, mirrors a cosmic heartbeat, its end a return to its origin, whether a one-time event or a cycle. The Big Crunch invites us to ponder the cosmos's destiny, a story written in gravity and energy. All right, moving on, and now, let's witness the dawn of cosmic light. Some 200 million years after the Big Bang, the first stars, known as population 3 stars, formed from primal hydrogen and helium, igniting the universe's first candles. These massive stars forged the elements that make life possible. So let's explore the science behind these primordial giants and their role in the cosmic story. Population 3 stars marked the end of the cosmic dark ages, a period when no stars shone. Only gas and dark matter filled the universe. Formed 100 to 200 million years post-Big Bang, these stars, lacking metals, elements heavier than helium, were massive, up to 1,000 times the Sun's mass. The James Webb Space Telescope seeks their faint glow, probing this era. These stars formed in dense gas clouds. Collapsing under gravity, as dark matter halos provided the scaffolding, modeled by simulations like Illustris TNG. With no metals to cool the gas, temperatures soared, birthing giants that burned hot and fast, living just a few million years. Their fusion created heavier elements like carbon and oxygen, essential for planets and life. Their birth was transformative. Before stars, the universe was neutral hydrogen, opaque to certain light. Population 3 stars' ultraviolet radiation ionized this gas, a process called reionization, making the cosmos transparent. The Hubble Space Telescope observes early galaxies, showing reionization effects, completed by 1 billion years post-Big Bang. How do we know they existed? Their fingerprints linger in metal-poor stars, like those in the Milky Way's halo, studied by the Keck telescope. These second-generation stars contain traces of elements from population 3 supernovas, confirming their massive, explosive ends. The CMB, mapped by Planck, also hints at reionization tied to these stars. Their supernovas were cataclysmic. Massive population 3 stars collapsed into black holes or exploded as pair instability supernovas, scattering elements across space. These explosions seeded gas clouds, enabling smaller, metal-rich stars like our Sun to form. The Event Horizon Telescope studies black holes that may trace back to these early giants. Future missions will reveal more. The James Webb Space Telescope targets galaxies from 200 million years post-Big Bang, potentially spotting population 3 stars light. The Roman Space Telescope will map reionization's timeline, refining our view of their impact. These efforts illuminate the universe's first light, connecting us to its dawn. These stars reshape the cosmos. Their elements form the building blocks of planets, life, and you, linking the cosmic to the personal. Their black holes may have grown into the supermassive ones at galaxy centers, observed by Chandra. Population 3 stars were the spark that lit the cosmic fire. Now, let's trace the rhythm of the cosmos. Early in its history, the universe's expansion was slower, as gravity from matter tugged against it, but dark energy later accelerated it, racing apart today. This shift, revealed by supernova observations in 1998, reshapes our cosmic story. So now let's explore the science behind this changing pace and what drives it. The universe's expansion began with the Big Bang, observed by Edwin Hubble in 1929. As galaxies recede, their light redshifted. Early on, matter, stars, gas, dark matter dominated, its gravity slowing the expansion, like a brake on a cosmic wheel. The Hubble Space Telescope's supernova data showed this deceleration in the universe's first 7 billion years. Dark energy changed the game. Around 5 billion years ago, this mysterious force, making up 68% of the universe's energy, began to dominate, accelerating expansion. Type Ia supernovas, standard candles for distance, revealed this speedup, earning a Nobel Prize in 2011. The Planck satellite's CMB data confirms dark energy's role, showing a universe now stretching faster than ever. Why did it slow initially? Matter's density was higher when the universe was smaller, strengthening gravity's pull. The Friedmann equations from general relativity describe this. predicting deceleration until dark energy's constant density outpaced matter's dilution. The Dark Energy Survey maps galaxy clusters, tracing this transition, confirming the shift. The acceleration is dramatic. Today, galaxies move apart at 70 kilometers per second per megaparsec, measured by Gaia. In the early universe, this rate was lower as gravity resisted. Future expansion, driven by dark energy, may lead to a big freeze, where galaxies vanish beyond our horizon, a fate probed by the DC experiment. This shift probes fundamental physics. Dark energy's nature, whether a cosmological constant or a dynamic field, remains unknown. Einstein's lambda term, reintroduced in 1998, models it, but alternatives, like quintessence, are tested by the Euclid mission. These studies could reveal whether dark energy evolves, altering the cosmic pace. The expansion's history shaped structure. Early deceleration allowed gravity to clump matter, forming galaxies, seen in simulations like Eagle. The CMB's fluctuations grew during this slow phase, mapped by the Atacama Cosmology Telescope. Today's speedup stretches these structures, isolating galaxies, a process observed by the Sloan Digital Sky Survey. Future telescopes will clarify the story. The Vera Rubin Observatory will map billions of galaxies, measuring expansion's history. The Nancy Grace Roman Space Telescope will probe supernovas at high redshift, refining dark energy models. These efforts trace the universe's journey from a slow crawl to a cosmic sprint. Okay, now let's gaze into a future where darkness reigns. In the distant future, after stars fade, black holes may persist for googles of years, slowly evaporating via Hawking radiation, standing as the last cosmic survivors. These enigmatic objects will dominate the universe's final era. So let's talk about the science behind their longevity and their role in the cosmic endgame. Black holes form from massive stars, collapsing under gravity into singularities where density is infinite, surrounded by event horizons from which nothing escapes. Stellar mass black holes, 10 times the sun's mass, and supermassive ones, millions of times heavier, anchor galaxies, observed by the Event Horizon Telescope. Their longevity stems from their stability, resisting decay far longer than stars. Stars have finite lives. In 100 trillion years, star formation will cease as gas clouds deplete, leaving white dwarfs, neutron stars, and black holes modeled by cosmological simulations. White dwarfs cool into black dwarfs over quadrillions of years, emitting no light. Black holes, however, persist, losing mass only through Hawking radiation, proposed by Stephen Hawking in 1974. Hawking radiation is subtle. Virtual particle pairs near the event horizon can split, one falling in, the other escaping, reducing the black hole's mass. For a stellar mass black hole, this takes 10 to the power of 67 years, far longer than the universe's current age. Supermassive black holes, like those in galaxy centers, may last 10 to the power of 100 years, a Google outlasting all else. This evaporation reshapes the future. As stars dim, black holes dominate, their faint radiation, the universe's last light, predicted by theoretical cosmology. In the Big Freeze scenario, they become the cosmos's final relics, scattered in a sparse void. The Chandra X-ray Observatory studies black holes today, hinting at their future role. The process probes quantum gravity. Hawking radiation links quantum mechanics and relativity, suggesting information may be preserved, not lost, in black holes, a debate fueled by the information paradox. Experiments at the Large Hadron Collider explore quantum effects, indirectly testing these ideas. Future detectors, like LISA, could observe evaporating primordial black holes, confirming the theory. Black holes' legacy is profound. Their formation seeded galaxies, as seen in Hubble's deep fields. Their evaporation may release particles that form new structures in a dying universe, though speculative. The James Webb Space Telescope studies early black holes, tracing their origins to population 3 stars, connecting past to future. The cosmic timeline is vast. After stars fade, black holes will merge, forming larger ones, observed by gravitational wave detectors like LIGO. Their final evaporation may spark quantum fluctuations, perhaps birthing new universes, as cyclic models suggest. These ideas stretch our view of eternity, with black holes as cosmic sentinels. In this one, let's ponder the force steering the cosmos' destiny, kind of. Dark energy, driving the universe's accelerating expansion, will decide whether it ends in a big freeze, big crunch, or big rip, an invisible force shaping our future. Its nature holds the key to the universe's end. Dark energy, discovered in 1998, makes up 68% of the universe's energy, countering gravity's pull. Observed through Type Ia supernovas by teams using the Hubble Space Telescope, it accelerates expansion, pushing galaxies apart at 70 kilometers per second per megaparsec. The Planck satellite's CMB data confirms its dominance, setting the stage for possible endings. The big freeze is likely if dark energy persists. In trillions of years, stars will fade and expansion will dilute matter, leaving a cold void as modeled by the Dark Energy Survey. If dark energy strengthens, a big rip could tear atoms apart in 10 to the power of 11 years, a scenario tested by the DESI experiment. A weakening dark energy might allow a big crunch, collapsing the cosmos. What is dark energy? Einstein's cosmological constant, a constant energy density, fits current data, but dynamic models, like quintessence, propose it changes over time. The Euclid mission maps galaxy distributions, probing its behavior. If dynamic, dark energy could shift the balance, altering the universe's path from freeze to rip or crunch. The stakes are cosmic. Dark energy's strength determines whether galaxies drift beyond our horizon, as seen in Sloan Digital Sky Survey data. In a big rip, space-time itself could fracture, ending all structure. In a big crunch, gravity's victory would crush everything, perhaps sparking a new cycle, as cyclic models like Penrose's suggest. Observations constrain possibilities. The CMB's flat geometry, measured by Planck, favors a big freeze, but uncertainties in dark energy's equation of state, studied by the Vera Rubin Observatory, leave room for surprises. Gravitational wave detectors like LISA could probe early universe conditions, hinting at dark energy's origins, possibly tied to inflation. Dark energy reshapes cosmology. It drives structure formation by stretching space, isolating galaxies, as seen in simulations like Illustris. Its discovery overturned expectations of a decelerating universe, forcing a rethink of Einstein's theories. Future missions, like the Roman Space Telescope, will refine measurements, narrowing the cosmic endgame. The mystery fuels wonder. Dark energy, an unseen force, governs a universe we barely understand, linking the Big Bang to its end. Whether constant or evolving, it holds the cosmos' fate, a puzzle that may redefine physics itself, uniting quantum and gravitational realms.